In this video, we will discuss stiff ordinary differential equations. Now, what are stiff ordinary differential equations? So an ODE is called stiff when stability criteria require the step h that you use in the numerical solution to this ordinary differential equation to be unacceptably small for standard explicit numerical methods. Now, this can occur in a lot of cases when your solution consists of two parts, where one part has very fast dynamics, and those fast dynamics, they tend to require a very small time step. But on the other part, there's also a component that has very slow dynamics. And these slow dynamics, this means that, well, at least part of the solution varies only very slowly with time or with x. So that requires a very long integration horizon in order to get to a steady state or in order to capture the main dynamics of your system. So this combination of requiring a very small step with having to cover a very large distance is what makes the solution of these stiff equations using standard explicit methods very, very expensive, prohibitively expensive even, such that for this always specific numerical methods will be used. Now, in practice, you can often recognize such systems whenever you have parameters that differ very strongly in their order of magnitude. For example, when you're looking at a system of chemical reactions or chemical kinetics, when you have a very large difference in reaction rates between different equations, such that one reaction occurs very fast, whereas another one is relatively slow. Another example, if you have a mass spring damper system, which has a small mass, but a very stiff spring. And this is also somewhat related to probably how these ODEs get their name, stiff equations, is that such a stiff spring with a very large spring constant let's say compared to a small mass, also causes your equations to be very stiff. Another example from electrical engineering is if you have a system or a circuit with very fast components, such as transistors, combined with very slow components, such as inductors. This also leads to very stiff system of differential equations in the end. Let's look at an example of a stiff ordinary differential equation. And here we have an initial value problem. So we have this ordinary differential equation over here, minus 1000 y minus cosine x minus sine of x, and an initial condition of 0, which you can solve exactly. So here is the exact solution. So we have one component minus e to the power minus 1000x plus another component cosine of x. And you can verify that this is actually a solution to this equation by taking the derivative and substituting it back into the ODE. But we see that we have two different components to the solution. So one very fast component. So this is a very fastly decaying component, e to the power minus 1000x, that goes to 0 very fast with x. Whereas cosine of x is something that, at least compared to this fast transient, varies rather slowly. So that has a period of 2 pi compared to the speed of this transient that is extremely slow. Let's take a look at stability criteria. And actually for this equation, well, you can rewrite this as a test equation plus a term that is only dependent on x and not on y. So then the same conditions for the test equation hold as for this IVP. So we can write this as the stability condition for explicit Euler for the test equation. So that's minus 2 divided by lambda, where lambda is minus 1000. So in explicit Euler, we find that the maximum allowable time step for a stable numerical solution is 0.002. And note also that, well, this has a stable analytical solution as well, because this is a decaying transient. so it doesn't blow off, or it doesn't go up to infinity or blow up or anything. So this is a condition for stability of the explicit Euler solution. Whereas for implicit Euler, we saw in the previous video that you can basically pick whichever h you want in order to obtain a stable solution there. That doesn't say much about accuracy. So for accuracy, you tend to want to pick an h which kind of resolves at least the important dynamics in the system. But in terms of stability, for implicit Euler, you can pick any h. So you could take an h of 10, 100, 1000, it would still remain stable. Whereas explicit Euler requires 0.002 at the most. So let's take a look at our example, and let's compute these things numerically. So what we have here is the initial tangent of the solution. So in blue, we have the exact solution, the analytical solution to our system. In orange, we see the explicit Euler solution with an h which is barely stable. So this is absolutely stable. So it's slightly below the limit of stability. And we see that initially, well, we have quite some wild oscillations, but they get damped out after some time. Whereas implicit Euler, and it's shown here with the green dots, we can use a time step which is about 100 times, well, it's let's say this is yeah, it's 100, yeah, it's about 100 times larger than the explicit Euler time step. And well, still it's a stable solution, so there are no oscillations here whatsoever. It looks very nice from a qualitative point of view. And also let's take a look at, well, what happens if we want to take a full period of the actual solution. So we see here that this fast tangent has decayed, whereas this cosine of x, it's actually nowhere to be seen in this solution yet. So the dynamics of the cosine have really not kicked in. And in order to get a clear representation of the behavior of this analytical solution, we need to integrate this for a much longer horizon. So let's say that we integrate it for a full period of the solution. So from x is 0 to x is 2 pi. Well, then we see that, well, explicit Euler, it has this requirement that we need to take time steps of h below 0.002, which result in over 3000 time steps, or 3000 x steps in this case, to cover a full period of the solution. Whereas with implicit Euler, for an h of 0.1, we can do this in 63 steps. Now, if you want, you can also do this in 5 steps. It's unconditionally stable. Your accuracy of implicit Euler will go down somewhat when you take larger steps, but we would still get a stable solution for implicit Euler. Now, this situation gets aggravated even quite a bit more when we, for example, look at what happens if we want to get a nice solution for explicit Euler. So these initial oscillations of explicit Euler, by staying close to the stability limit, well, that's something you don't really want to see in your numerical solutions. So let's say that we take a much smaller h still, such that these oscillations do not occur in practice. Well, then covering this full period of the solution gets even more expensive. So here in this case, well, this would require you to do more than 6,000 steps. So these stiff equations are really the bread and butter of implicit solution methods, because they allow you to take rather large steps while still attaining, or let's say still inheriting, the stability of your original analytical initial value problem. And that's the main, I think, the main attraction of these implicit methods.